Good morning. We have yet another Codeforces round. Here we go. It is Global Round 17. Should be very fun. And additionally, we got a little camera monitor. That should be good. I'm going to be doing it in Java, and at the end of the contest, I'll have solutions to all the problems that I know how to solve. So let's jump into the contest. I'll see you on the other side. What do you say? All right, we have given an M by M grid. We do some cell, we have to determine which one. We have to choose some K cells, give them to the computer. In response, we will get K numbers. This is the Manhattan distance to the hidden cell. How big can K be? After receiving these, you will be able to determine the hidden cell. So it's either 1 or 2 always. So you can always pick top left, top right. Yeah. That one case is a little silly. Move on. All right, we have an array B, which is a palindrome. We know what a palindrome is. All right, we got A. An array is called a palindrome if it's possible to select some integer x and delete some of the elements of the array equal to x, such that the remaining array is a palindrome. Note that you don't have to delete all elements equal to x, and you don't have to delete at least one element equal to x. So both of these statements are worthless. We might as well. Yeah, so like, is something a palindrome? Man, this is a hard div 2b. Is something a palindrome if we might as well delete all instances of it. Okay, I don't see it. Move on to C. Cashew's throwing himself a party. He wants everyone in the party to be happy. He has N friends. The ith has I dollars. You want to invite the ith friend to the party. If you invite the ith friend to the party, he will be happy only if at most AI people in the party are strictly richer than him, and BI are strictly poorer. He wants to invite as many people as possible. Find the maximum number of people he can invite so that every person would be happy. You can always do 0, lots of people. If at most this many, and at most this many are poor. Okay, so each person has the I friend has I dollars. Okay, so you can have like at most A before you and then B after. So I guess what, you'd go from left to right. You could take this if you want. Man, this is a hard contest. Holy cow. That was a very difficult contest. Yeah, look at this delta. Oh my goodness. Okay, I guess we'll bring out like the big guns for B, see what happens. Yeah, we can do a hash and then a hash backwards and then skip indices of a 3. When is something not a palindrome? Oh wait, the thing you delete has to either be the first or the last. Yes, okay. So yeah, you either have to delete the first one or the last one. Unless it's the same, in which case you can maybe delete this, but you might as well just ignore it. Yeah, if it's the same, ignore it. So now, first to the last, okay. And then delete it and then check, okay. So this is easy. All right. So how do we actually implement this? Probably something like, well, I1 is less than I2, and 8I1 equals 8I2. This, and then we need I2 is greater than or equal to 0, and 8I2 equals to remove I2 minus minus, and then we'll just make this true. skip the things we don't care about, do this, and then if a at I1 is not equal to a at I2, then return false. Okay, otherwise which ones do we have to skip? So yes, we've skipped all the ones that matters. So if I1 is greater than or equal to I2, then as we check both ways of doing it. What is this? Oh, otherwise. To remove is 1. I2 minus minus, but that should never happen. Oh yeah, I could maybe. All right. That was a good problem. Yeah, that was good. All right, problem C. We have n friends, ith friend has I dollars. Yeah, this one. So, okay, so the idea here, oh man, let's go back. We've got some things happening. Each person, as we invite more people, like each person is invited for what happens, I guess. So you start getting invited. And then you also stop getting invited. So when do each of these things happen? This happens when there are too many after you. When do you start getting invited? Well, I guess you're always invited initially. Oh, when there are, yeah, so when there are like not too many before you. I'll suppose we know the answer. I guess if we know the answer, it's easy. Yeah, so we binary search the answer, and then you just iterate through. Yeah, okay. This is a really good binary search problem. This is a really good. Because this is like, you don't see it right away. I mean, I don't see it right away. Maybe I'm being a little silly here, but it's good. Max equals n. Yeah, so we do some stuff. And then we print the answer. Possible, that means min equals mid, else max equals mid minus 1. So we need a plus 1 here. And then static Boolean possible. P.A is less than used, and continue. Otherwise, if P.B is less than target, continue, target minus 1. Okay, otherwise target minus minus, use plus plus. Two, one, oh, why is this? Why would this be? A used is less than used. Wait, is this bigger? Oh. Okay. Hacky way of doing this, but it works. Yeah. Okay, not much harder than B. Alright, that's good. Alright, be right back. Lee couldn't sleep lately because of flavor text. Too much flavor text gives you nightmares, right? A non-empty array is called good if there exists an integer, if there exist m integer sequences which satisfy the following property. The ith sequence consists of bi consecutive integers, where the ith can be plus or minus 1 or 0. Oh, or 5 minus 4 minus 3. What? Oh, 3 consecutive integers. Okay, gotcha. Or bi consecutive integers. Assuming that the sum of integers in the ith sequence is sum I, we want sum 1 plus sum 2 plus sum m to be equal to 0. Okay, so you have a bunch of things. You're going to choose a bunch of sequences. Each are consecutive integers. Then you want the sum of all of the numbers chosen to be 0. We're given an array which has, okay, lots of subsequences. Count how many of them are good. Huh? What on earth is even happening? Okay, we have, okay, so this is how we tell if something is good. So for each subsequence, we want to say, is it good? So what does it mean for something to be good? There exists m integer sequence. So we can pick a bunch of sequences of integers. Of these lengths. And these things sum to 0. Okay. So like, so 2, 7 is good. Oh, because you can have minus 4 to 4. So does this mean how many subsequences have odd sum? All right, sanity check. If you have odd sum, it is possible. Yeah, because you cover a range including 0. What if you have even sum? That means if you have an even sum, it's probably not possible. Both of these have odd sum. Yeah, so I guess we'll use that assumption for now. Like we want, the solution here is like we want to count how many subarrays have odd sum. So we have like n evens, so we have 2 to the n evens. For each one of those, we can choose any number of odds. So we have like n choose 1 plus n choose 3 and so on. Yeah. Okay. So this is something I really need to do with my life, which is get this mod stuff under control. So we have add, multiply, fast pal, long base, long exponent. If exponent is equal to 1, return 0. Otherwise, long half equals base times, or no, equals fast pow, base exponent over 2. If e mod 2 is 0, return fast pow of, no, return multiply of base and base. Otherwise, return multiply of base and multiply half in base. Okay, so we have that. Then we need pre-comp. We need our pows. Oh, wait, what is this? These are factorials and then inverse facts. Multiply I by facts at I minus 1, and then inverse facts at I equals fast pow of facts at I to mod minus 2. And then if facts at 100 by inverse facts at 100 is not equal to 1, then throw no. Okay, or facts at 3 is not equal to 3 is 6. 6 times 3 is 9, right? 2 times 3 is 6. Yeah, good. That's what I meant. Okay, so this should check here. Now we need to pre-comp. And then we need to choose K. Facts at n by multiply. This is an int, I guess. Facts in facts at k, in facts at n minus k. All right, so we have that. So sys out and choose k. Let's say we have 4 things. We want to pick one of them. What? Okay, 4, that's right. Good. So we should be good with our base calculations here. Now we can actually start the problem. So that all should have been, how much time did I spend on that? Like 10 minutes? That all should have been a copy paste. So that's an improvement to make for next time. You get better. Single test case, I think. Reverse size n. Int n even equals 0 and odd equals 0. So we have counts. Long ants equals fast pow of 2 to the n even. And then 4 into I equals 1, I is less than or equal to n odd, I plus equals 2. Wait, can we choose 0 odd things? We can. So you can choose, you can have an overlap at 0. Yeah. Is it two things that are the same? Maybe, not necessarily. So you can have any odd sum. You can have I guess you can have an even sum that you can split in 2. I guess you can have anything and then a 1. Because if you have the 1 can either pick 0 or it can be in the end. Okay, let's do this 2, 2, 4, 7 thing. So we have 2 to the 3. This is 8, right? 2 to the 3 is 8. You're telling me there are only 2 more things? We can do 2 and 2, 2, 2, and 4, and 7. Oh, the 7's included. Which ones can't we do? A 2 on its own. And a 2 and a 4. Or does that, can you do any 3 evens? Let's make this one 0. I don't think you can do 2, 4, 8. I don't actually know. Let's call an array of k integers terrible. The average of these is equal to k. Oh wait, let the average be this. Okay. And the number of elements which are bigger than the average is strictly larger than the number of elements which are strictly smaller. Yeah, okay. Let's call m integers bad if at least one of its non-empty subsequences is terrible. What is a subsequence? Did they just tell us in the last problem? Yeah, deletion of some elements. This sounds kind of wacky. You probably can't have that many things. Okay. So that sounds like doable, but kind of hard. Maybe let's try problem D again. So what is the sum of elements? So we'll have like 0 plus 1 plus 2 plus 3. This is n times, so n is 4. So it's n times n minus 1 over 2. Then we can also add k times n. Oh, if our array has any odd numbers, then we're fine. The problem is if all numbers are even. Yeah. So all are even. What do we do in that case? Because if you have 2 odd numbers, you can always delete one of them. All the numbers are even. Do we need 2 equal subsets? Are you really telling me there's no sum of 4 elements that's equal to the sum of 2? Really? There's no sum of 4 consecutive elements that's equal to the sum of 2 consecutive elements. So this is like 2 times 2 minus 1 over 2. What does this equal? Times like k times 2. This is not true. That's just an odd number. It's any odd number. You can do 2 and 4. Which numbers can't you do? Just 3 evens? What? You can do 2 and 4. You can do, so what's 4? So you have 0, 1, 2, 3. So this sums to 6. Oh. But the two things will be odd. Okay, so you can pick, if you have at least one odd, you're good. Otherwise, then wait, so 4 and 2 doesn't work. Is that because 1 and 2 doesn't work? 1 and 2 does work. Why does 4 and 2 not work? Four and 2. Because this will have odd sum. And this will have sum modulo 2 equal to 0. So it isn't possible. So if we have if we have like any odds, then it's good. Otherwise, this means we have all evens. Wait, so can we get any? So 2 is like 2k plus 1. 4 is 4k plus 2. What is 6? 0, 1, 2, 3, 4, 5, 6. Or wait, 0, 1, 2, 3, 4, 5. So add up to 6, 3. Yeah, so 6 is 6k plus 3. Okay. What does this mean? So 2 and 6 works. What the heck? Where do you even start? You can, okay. We have all evens, or yeah, so all odds. I guess all evens is the hard part. If we have a 2, this will give us any 2k plus 1. 3 will, or 4 will give us 2k, 4k plus 2. 6 will give us 6k plus 3. Is it ever possible to have an array of size 3 that doesn't work? Yes, 3 evens. So let's try 16, 10, and something else. So this will be 16a plus 8. This will be 10b plus 5. This will be a lot. Is this the GCD of 16 and 10? Yeah, I guess you can get the GCD. You can get any multiple of it. So 2. What does this look like for odd numbers? 1, 0, 1, 2 is 0. 0, 1, 2, 3 is, well, 3, 4. So mod 5, 0, 0. Okay, 0. Yeah, so odd numbers just go to 0. So we can add any GCD of the chosen elements. This is a hard contest, I'm telling you. And I'm still going up. That's scary, dude. That's scary. Oh, man. This is like the equivalent of like a div 1b here. So we can add any GCD of these elements. We need to get sum over 2. Okay, so this is going to be this mod 2. The GCD mod 2 is equal to 0. So this is a multiple of 2. If this is also a multiple of 2, what does that tell us? Well, if it's not a multiple of 2, then it's not possible. So if sum mod 4 is equal to 0, it's not equal to 0, does that mean impossible? You're telling me 2, 2, 2 is impossible. 2, 2, 2. Guess so. Or, oh, you can make this. You can't make it 3, 2. Okay, what if the sum is equal to 4? Mod 4 equals 2. Well, this is equal to 2. So what if the sum mod 4 is equal to 0? Probably just true. Okay, so what have I, let's take a step back here. This is a bit sketchy. What am I doing? So I know the sum, or okay, so I know if there's any odd number, we're good. Yeah. So any odd, then it's good. Why? Because we can delete as many odds as we want for free. And when we have one odd left, the sum will be odd. Okay, so this is proven. So the question is, when we have all even, and then the sum mod 4 is equal to 2, then the answer is bad. Because, why is that the case? Because we need because we can only add some multiple of 2, but we have to hit an even number so that parity doesn't work out. Okay, so what if we have all even, sum modulo 4 equals 0? It's not necessarily good or bad. Could be either. Could definitely be either, because you have 2, 2, and then you also have 4, both of which are in this case. So what if you have any, so I guess if you have the GCD equal 2, Oh, I guess then you divide everything by 2. Let's start over. Divide all by 2. Oh, goodness. Does that work? That would be so cool, wouldn't it? That would be so cool. Then we have like the same problem, but it kind of doesn't work. How many odds? We need to have an even number of odds. We can have like some solve with like some array. So either we need an array, and then also whether this is like the root. Okay, so the root case is do this thing. Otherwise, we can take any even number of odds, and then any subset of evens. Yeah. Okay. This is a bit of a stretch here, but we can try it. So I plus equals root, if it is root 1, otherwise 2. Oh wait. Okay, so if we're the root, then let's do this. So if for the root we do one thing, otherwise we do another. So for the root we can pick greater than or equal to 1 odd, or 0 odds, and then recurse. Alright, so then long odd ways would be n choose k. This is, we have n odds, and we want to pick I of them. So then ants equals add of even ways, and multiply, or I guess add ants, and multiply the even ways by the odd ways. Okay, so this should handle that. Yeah, inches 1, inches 2, inches 3, etc. Okay. So that happens in that case. What happens when, oh wait, we also can choose 0 odds and recurse. Okay. So this will be an evens. Build this new array. Otherwise, we choose none of the odds and a subset of evens that works. Man, I just like cut my lip open here. Oh well, it'll be a bloody mess. Okay. Cool. Otherwise, we must choose. So we can choose. We can choose any odd number of evens. This is way too complicated of a solution to be right. Okay, I guess we'll just finish it up and then try it because we're pretty close, I think. And choose any odd number of evens. No, choose any even number of odds. Choose an even number of odds and then stop. I don't know that this works, is the problem. We choose any even number of odds greater than or equal to 2. Okay, so if this isn't the root, what does this mean? If we choose numbers with an odd sum, that means it's impossible. So when is it possible? So we probably just want this still. Non-empty. Am I missing one here? Hold up. Hold on a minute. We have... Oh, no, that's fine. There are indeed 8 there. Yeah. Okay. So, for the root, we can pick greater than or equal to 1 odd, multiply by even ways, and then we're good. All right, or we can pick none of the odds, everything's even, and then we solve it here. Okay, otherwise, if we pick an even number of odds, then it's, or if we pick an odd sum, it's impossible. Yeah. So a working subset of evens. So this will be solve. You can pick nothing, right? Yeah. Yeah, okay, so solve of new A, not the root. So this includes the 1. So long odd choices. So there are this many ways to pick any even number. And then I think that's it. Oh boy, that was way longer than it should have been. I don't even know if it's right is the problem. Okay, so what if everything is even. Yeah. Nine. Why 9? Why 9? 9 should be 10, but I don't think it's the -1 that's killing us here. All right, so we have 2, 2, 4, 7. So we can take the 7, and then we have 2 to the 3. So this gives us 8 ways. Or we can take the 1, 1, 2. Without the 7. What about the 1, 1, 2? Okay, so there is not one way of doing this. There are 2. What are the 2 ways? So this is all ignorable. So it's solve of 1, 1, 2. Because picking the 1s matters with the 2. I still don't even know what is legit and what isn't. Move on to E. All right, time to get some new paper. We might come back to this, we might not. All right. Okay, so we have an array. It's terrible if the average is bigger than the number of elements smaller than the average. So what does this mean? So it's bad if the average is bigger than the average, strictly larger. So if you have 1, 4, 5, 6, what is the average of these? Well, I guess multiply each number by 4. So then you have 4, 16, 20, 24. And then the sum is 10 plus 6, 16. Right? Yeah. So 1, 4, 5, 6 is terrible. So, wait, what? Yeah, what makes something terrible? I guess... Man, this is like kind of hard to predict. Find the minimum number of elements you have to delete to make a good array. So there's going to be almost all of them? Yeah. Would it always be the min and then the biggest 3 of them? Well, what is 1? Oh. You can delete the 1. Is 8 the biggest 3? Oh, what if we want the biggest 2? So 1, 5, 6. Look at that, 1, 5, 6. So the average of this, okay, yeah. The average of this is less than 5. It's the average of, yeah, it's less than 5. So this is a delta of 4, this is a delta of 1. So you can have a delta of 1, and then another delta of 1 if you want, and then you can have a delta of 2. then 4, and 8, and then 16. So we'll get this problem eventually. Is it worth a lot of points? No, not many. Yeah. So otherwise there's a group of 3 that would be terrible. Is there something better than the naive DP here? We have like DP at like last taken, and then the gap. Oh, really, we just need the first. Yes, this is like an n squared. So for this, you have just the 1. Well, for the 6, you just have just the 6. For the 5, you have just the 5, because you would go to 10. Or you would go, this is a gap of 4, you need a gap of at least 4. So you would go to 8. So 6 would be plus 5, which is to 11. 5 would be plus 4, which is to 9. 4 would be plus 3, which would be a 7. And then it's the range max. And 1 would be just 2. So this works if we know what the minimum element is. Oh, I guess just do the DP the other way. So we have 1, 2, 3, 4, 5, 6, So for 5, you can either start here, or if you're going to take 5, it depends what the start is. After the bathroom. If you take some integer, the next thing, like you can't take anything smaller than it minus the smallest. Now, this is an easy problem. I just don't know how to solve it. Okay. Like you can pick X and then your start. So really it's like you can pick anything in this range, but once you do, like the things you can pick extends by different amounts depending on where the start point is. This is an n squared dp. How do we make it faster than n squared? Can we do like some n root n? So yeah, I guess we have a couple approaches here. And how am I doing? Probably pretty terrible, right? Yeah, pretty bad. Pretty bad. Man, is D really that easy? Oh my goodness, Rainbow. Well done, Rainbow. Well done, my boy. Okay. Should we just brute force this to find? We still don't know. Are there even any groups of 3 that don't work? Yeah, there are. Okay, let's go back to this. So for groups of 3, there's 4, 4, 2, right? This is impossible. Because this has an even sum, this has an even sum, this has an odd sum. But 2, 2, 4 is possible. So when we recurse, we would need to know, if you get rid of the 2's, we know everything's value mod 4 is equal to 0. We need to know a bunch of stuff though. Yeah, so we need to pick things with an even sum. Why? Yeah, so yeah, need to pick things with an even sum. What if we need to pick at least one thing? Is that it? We need to pick things with an even sum and pick not just one thing. No way, that's it. Yeah, you can have 4, 8, 8. So this is going to be 2 mod 4. This is going to be 0 mod 4. This is going to be 0 mod 4. So the sum mod 4 will be 2. I'm not seeing it. I don't see it. I don't, maybe it's not just powers of 2 also. So, okay, sanity check, you can have large groups of things that are impossible. Or at least things of size 3. Can you have any of size 4? Oh, man. Probably. Yeah, you can. Just add another 4. 4, 4, 4, 2. Or wait. Yeah, you can. Oh, this is just like a math problem. So you've got like n times n minus 1 over 2. Modulo k times n. If n mod 2 is equal to 0, So this is just n over 2. So the sum of like values AI over 2 modulo the GCD of AI is equal to 0. Right, because this is the target, and then this GCD is what we can shift by. Yes, this is the case. How many choices for the GCD do we have? Oh, I guess, yeah, what if we knew the GCD? There are n log n possible GCDs? No, there are more. Well, there aren't that many. There's n times cube root of n. So n to the 1.3. GCDs? Because everything's a factor of something? Cube root factors? Yeah. So n to the 1.3 GCDs. Let's say we knew what the GCD was. We need to pick a sum modulo the GCD that's equal to 0. There are a lot of sums. And the GCD can be pretty big. Yeah, GCD can be like up to like n over 4 and still be confusing. Like 10 to the 9. This problem is so hard. Ah. I don't know. Okay, back to this one. So, yeah, we want to pick the max things from an array. So that, oh wait, 144. We can't have 144. Yeah. Okay. Pick max things from array so that like differences are always like this. Oh, so you just like literally take the next one. So brute force start greedy. Oh, this problem's a banger. I guess we might as well sort. Alright, and then we need a tree set. Alright, so int next. Okay, so int it'll be curve val plus curve val minus start val. Oh, I guess curve val equals just ts dot higher of curve val. So start is n minus 1, then break. Okay, otherwise we get the next highest thing. Curve val equals the next thing. Count plus plus. Okay. So, and while true. Oh, sorry, val. Okay, so while they're in next, min will be curve val plus curve val minus start val. And then min equals math.max. Okay, if ts dot higher of min or that ceiling is equal to null, then break. Otherwise, curve val equals ts dot ceiling min and count plus plus. Not TLE here. What? What? No. No. Was this really it? Okay. So this will be okay, so then we need to get the next thing. So if A at mid is greater than or equal to then max equals mid. Otherwise, min equals min plus 1. Dude, Java. Okay, still not great. Tourist isn't solving F. Okay. All right. So that means our contest is problem D, right? Yeah, that's unfortunate. This problem's gonna be the end of me. Okay. That felt very satisfying. There's got to be something I'm missing. Okay, that's called kind of gross. Try again. What is going on with this problem? So a good subsequence okay, we've got an array. We want to pick some of the elements in the array. We want there's some, okay, so we either want greater than or equal to 1 odd, or we want all even, and then we want their sum over 2 to equal their, or sum over 2 modulo their GCD is equal to 0. All right, so the GCD might be 2. Okay, GCD equals 2 or not equal to 2. If it's equal to 2, that means we pick at least one element here. Modulo 2, yeah, okay, I got it. To be fair, let me just say, this problem is much harder than problem E. But yeah, I got it. Okay, so here's how you do it. So you can pick at least one element. I'm just like BFS to the path of the, or like DFS to the path of the solution. I have to make sure it's legit, but this will be right. So we can pick at least one element mod 2 mod modulo 4. And if that's the case, then all we need is, yeah, for each of these, we need some mod 2 equals 0. Yeah, if it's not equal to 2, that means we pick 0 elements. And divide everything by 2. Okay. Let's get problem D. So, option 1, either we pick at least one odd or 0 odds and recurse. Yes, so this is at least one odd. This is 0 odds. Okay. Otherwise, so this is, well, that's kind of dumb, but anyway. Okay. So delete this. What are we doing? Okay, so either we can pick wait, maybe I haven't solved the problem. So we can pick yeah. Okay, so this is 2. Okay, so yeah, either we can pick maybe we just don't want to include this case. well, whatever. Or we can pick so if we pick 0 odds, we get this. Pass power 2 to the and even. I guess we already have this. Odd ways to the even ways. So this is if we pick at least one. This is add. So at least one even and any, or at least one odd, any evens, or this one is the other case, which is all evens. Let's go. That's an amazing problem. Dude, this is like one of the first times. What? No, I didn't. You're kidding me. You're kid that you cannot be serious. What? I can TLE test 1. What? 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 Give me a 2-second time limit. For the love of God. Ah. TLE test 1. All right. Are we looking standings wise? Rating change, please. -8. Not terrible. Let's get another problem. Okay. That's literally the most satisfying thing. I love it. I'll clean it up after for sure, but still. Lee was planning to get closer to some flavor text, but then decided that he should do the problem instead. Marsh-Talley's graph is an undirected weighted graph of n vertices and m edges, each with weight 1 or 2. Lee wants to direct the edges of Marsh-Talley's graph so that it will be as beautiful as possible. The beauty of a directed weighted graph is equal to the number of Odyssey. I don't think that's how you spell Odyssey. Is it? It is. Okay. I'm wrong. The number of Odyssey vertices. A vertex is an Odyssey vertex if, what the heck? The sum of weights of outgoing edges minus the sum of weights of incoming edges is equal to 1. Okay. So if it either has one more outgoing or one more incoming edge. Wait. Find the largest possible beauty of a graph that Lee can achieve by directing the edges of Marshall's graph. In addition, do it. Okay. Is it always possible? It's always possible. It's always possible. Wait, what is output? Wait, what? I guess it's not always possible. Yes, it is. Surely it must be. What is the beauty? Wait, only 2. Versus 2 and 5? Oh. Oh, okay. One and 6. 1 and 6. Yeah, everything else is even. Okay. Yeah, so all right, so this is flow question mark. Yeah, so surely the answer is like the biggest it can be, right? So you might as well, might you? I don't know, it's kind of tricky. What if we get rid of all 2s? Yeah, if we ignore the 2s for now. Let's handle the 2s later. So now we have a graph where we're going to do some stuff. So any node with even degree we can ignore. Otherwise, we choose some path, right? Yeah. Otherwise, like choose a path from odd to odd, and then flip all weights. Okay, now the problem is 2s. Yeah, okay. So the thing here is we still have choice because we now have like this thing where this can go this way or it can go the other way. So we still do have choice. And we're going to use this to make sure we pick this and the 2s in the opposite way. Like we have 2 choices. We want to make them align. So if we have some path like this, we can go here. Oh wait, what if it's not connected? Oh, it will be connected. Like within a component, it'll be connected. Okay, after the bathroom. Okay, so we can do something like what was that? The light just flashed. We can pick like a path, remove a bunch of one edges, make two things odd. So, well, do we want to just do that in the beginning? But we might need to flip a path. Wait. Oh yeah, we print the directions. So yeah, if we've got like this, it kind of works. Like we have an issue of if this is a 2. So this might be like 1 minus 1. Oh, if we just set this to 1, then what happens? What about this? Yeah, so we can like can turn this into a graph where each node has degree at most 1. But now you have these weird like edges between the middle of these paths. And like the paths intersect. Oh man. Oh well, I guess this doesn't matter. Yeah, so all of these nodes we don't really care about. And then all the nodes in the middle we also don't care about. If it's something like this, we care about half of it. And if it's something like this, we care about both parts. Yeah, okay, so we like make these paths. How much time do we have? We have 39 minutes. Okay, so we can ignore any twos not hitting greater than or equal to 1 like actual node. Okay, so now we can hit some node. So if we hit just that, we hit just 1, oh, if we hit just 1, we just like choose the direction accordingly. Yeah. Then we choose the direction. Okay, so if we hit just 1, that's fine. The problem is, what if we hit 2? Oh. Yeah, if these are the same, and then we have a 2 like this, so we have to keep them different. Yeah, what do we do about that? So they have to stay different, yeah. Do they have to stay different? Yes, they have to stay different. Okay, so they're different if there are an odd number of 2's connecting. If there are an odd number of 2's connecting them, okay. Even? There are even number of 2's connecting. So initially they're different, then they become the same, and then different and same. Okay. Yes, this is turning into 2 sets, potentially. Wait, no. If you have a 2 connecting, then they stay different. So yeah, if we connect these with a 2, then that just flips them. Okay, what if you connect something like this? So what if we have a 2 like this? Then we have a problem? Problem, question mark? No, so then we can make them the same because we've already handled all of these. Then we like possibly flip everything. And then add the edge. Possibly flip everything. Yeah, because if you have some graph, flip all the edges, it just changes the plus ones and minus ones. Yeah, that's annoying. But it works. Yeah. Okay, let's go through this one more time, make sure we have an actual idea. And then, you know, just for good luck, okay. So we first get paths. Of 1 edges. Okay, so now we have a bunch of paths. So from this we've got like a paths list, and then we have a bunch of like start ends. Yeah, start end pairs. Okay, so we've done that. Then we handle all 2s. Handle same 2s. This will be easy. Okay. Okay, so now we've handled the same 2s, that's fine. The problem is, what about the different 2s? Then the different 2s don't matter. Yeah, like flip everything if required. Yeah, okay. I think we can do this. It's going to be tight on time, but we can give it a shot. This is problem F. Probably not. We'll just leave this for now. All right, so this has node from to and cost edge. Okay. Single test case, yeah. All right, so then we want public void. Oh wait, do we actually want this? We should probably just make this the one edges. All right, so yeah. So then for node nn in nodes, if nn dot one edges dot size mod 2 equals 1. Do we want to flip literally everything? We might as well. Well, I guess we'll see this in a minute. So 27 minutes left. So we're DFSing here. So for each of these one edges, DFS from this guy. Oh. So if e.used, we don't care, or we can skip it. Otherwise, it's not used. So e.o into use, pass in this, and then go use it. So then we'll use this other edge. Yeah, okay. And then return. All right, otherwise, none of this happened. So now was and equals true. So this will be from an end to end. Okay, so this will handle. Okay, then we need two edges between. What things do we have? So we have the same twos. Yeah. So we probably want node, we'll call it spouse. So then nn.spouse equals end, n.spouse equals nn. Oh, these can be the same thing, can't they? Can they? No, they can't. Not the same thing. Because everybody is straight. Yeah, everybody's straight. They're all different colors. Your spouse is always different. So far, anyway. Okay, so that'll change in a minute, but as of yet, still true. Okay, so then how much time? 20 minutes. I think we should still probably be fine. So for edge E in edges, if E dot cost is not equal to 2, then continue. If E dot from, oh, Okay, so we have these edges. If e dot from dot was end, okay, then we don't care. If e dot from dot was end and e dot to dot was end, else, then 1,2's dot add e. All right, so otherwise they both were. So if e dot from dot spouse equals e dot to, then same 2's dot add e, else different 2's dot add e. Static Boolean value inverted is false. Boolean positive. So flip all, this will say value inverted equals true. Static void get positive. So we should be good here, I think. Yep. All right, so now we have some stuff happens. We've got this stuff. All right, for each edge, yeah, so now, okay, so we need to handle this. So nn dot is positive going out, plus the plus is outgoing, okay. So nn dot positive equals, well, set positive nn, true, set positive end to false. Okay, so now for edge E in same 2's, then we do E, oh, if E dot what I call this is positive, E dot from, this is positive, then we have a problem. So then E dot go and use from E dot to, else E dot O and use from E dot from. In this case, set positive from E dot from to false, and set positive from E dot to true. Okay. So we've handled all of the same twos. Edge E in different twos. Oh no. This is broken. Shoot. What did I say for different twos? Yeah, they could be like this. So we might need to flip just one component. Because when you do this, if this is if they're both positive, we're in trouble. Okay, so this needs to be a disjoint set. Disjoint set, disjoint set, disjoint set. Yeah, disjoint set. Not really a disjoint set. Okay, so what do we need to flip? Just the path, right? Okay, so do this. This will handle this, I think. So now, wait, so this is handle the one edges. Yeah, and then for node and then in nodes, and then .dfs. This should get back to ourselves. Okay, so yeah, do this. So now we should mark all of the edges. Yeah, so this will hit all the edges. All right, so we do some DFSs here. Each one will have a new cycle num. And then, yeah, so Boolean. Cycle num. All right, so flip all and comp. This wasn't even right. Flip this is position node n. What the heck? Cycle num? Yeah. All right, so we need to set the cycle num here. Okay. Okay. All right. So if is positive at e.from equals is positive at e.to, then what is it? Flip all at e.from cycle num. All right, and now if is positive at e.from, then we want to go from e.o and use from e.to. Yeah, set positive at e.from to be false. .to be true. This will join them, won't it? This doesn't flip everything. Darn it. Yeah, this doesn't actually flip everything. Because we have, it won't flip these edges. Did flip the paths. You gotta connect these. Then you'd have A, B, A, B. Wait, how do you handle these? If you have this and this. Wait, then these turn into the same. Do they turn into the same? Oh, damn. Why? I'm so close. Do they turn into the same number? Kind of, but not really. I can't flip anymore. Right? Because we have to... Yeah, this isn't working. So the same twos are fine. The different twos have the problem. And then the 1-2s will be fine. These we can handle. So this is the only part of the problem that is a little messy at the moment. This flip is not compatible with the fact that we're adding an additional edge, which doesn't get flipped. Oh, we could just take the paths in the 2 graph as well. Darn. Out of time. Okay, successful hacking attempt on A. Could be the 0 case. Oops. Yes, we can. Oh, we can maybe try hacking. Looks like they've got it, yep. It's probably in pretests, because there are literally 3 cases. Wait, what was that? Yeah, that's fine. How do you hack A? Wait, return, oh. Yeah, that's fine. Alright, I'll take your word for it. I guess contest is over. I guess, yeah, other people in the room are probably looking for the same thing. Okay. Yeah, I should solve F. It's good practice, for sure. All right. Solution time? Solution time, I guess. So, okay. Yeah, let's talk about solutions. For problem A, the idea so for problem A, you have an n by m grid, and then what you can query is like, get me the distance to like between two cells. Yeah, so you have a query like this. So, oh man, that's kind of annoying. All right, guess we're using Paint instead today. So yeah, you can say like, if you have this cell and this cell, you can, where this is like the cell the computer picked, so the computer will pick one cell. And you can like pick one cell and then it'll tell you the Manhattan distance to that cell. So you can always get the answer if you query the top left and top right cells. So you can always do it in two. Sometimes you can do it in one query. And the way that happens is like, if it's just a single line and you query just the first element, then you know which element it's going to be. And obviously if there's just one square, you don't have to query anything. You know it's going to be that. So those are the three cases that just look like that. Yeah, so it's pretty easy. Somehow people are getting hacked occasionally, but I don't know, maybe they're forgetting the zero case. It's not too obvious. For problem B, oh yeah, this is a pretty cool problem. So in this problem, you have like an array, and it's a palindrome if the ith element is equal to the last element in that position. Nope. So yeah, we've got like some array. So it's like this. Here's our array. And it's a palindrome if the first and last elements are equal, and the second, like these elements are equal, and so on. But it's possible that there are some elements that are all equal to like the number 3, for instance, and it's these ones. And if you remove all of these, you have a palindrome with what's remaining. So the first and, in this case, fourth elements are equal, and the third element is equal to itself. And yeah, you want to see for some given array, is there any number you can remove that would make it be a palindrome with as many as possible of those numbers removed? It doesn't have to be all of them. It doesn't have to be in the array even, but it turns out like it should be pretty clear to see that if you're going to remove an element, you might as well remove all of them. Why is that? Well, some element's got to match with itself, right? So if it does, and you remove both of them, then everything in the middle will stay in the middle, and everything on the outside will still match with itself. So you might as well remove all copies of it, and you also might as well remove something in the array, because like if there is nothing that matches, you just pick the middle element and remove it. So yeah, that's the idea. And the question is like, does it work? So the key observation here is that if the first and last elements are equal, then you can just solve the problem on this middle part of the array. You can just ignore everything but the first and last elements, right? Like if these are the same, then just ignore them. But if they're not equal, that means one of these elements has to get removed. If neither of them do, then the first element of the array won't equal the last element. So we can immediately, if they're different, we can immediately say, we know the thing that gets removed is either this first thing or it's the last thing. Otherwise it won't be a palindrome. So we can just try both of those and then check if either of them works. And that's the answer. Yeah, so this check method, implementation-wise, this check method will just say, for some array, if I1 is the start and I2 is the end, and you remove to remove, is it a palindrome? And this will just like keep moving the I1 pointer as long as you need to, keep moving the I2 pointer as long as you need to, and then check if it's a palindrome. Otherwise, and then the other thing I do is I say like, okay, start this array, keep skipping the things on the outside as long as they're equal, and then start once I have a good solution. So this will run in order 2n time, which is fast enough for this case. All right, that's problem B. Let's move on to problem C. Maybe. Okay, yeah. So problem C, you have some party and one of your friends is going to, well, one of your friends is throwing a party and he has a bunch of friends. Each friend has a maximum number of people who can be in front of them in line and a maximum number of people who can be behind them in line. And yeah, as the problem tags say, the idea is just binary search. So once you know, like the question is like, is it possible for this many people to come? Rather than asking what is the most number of people who can come. If you just say, can this many people or more come, you can solve that pretty easily. So the idea is, you know that people don't change their positions in line. So you've got like some people, and if you know there are going to be 7 people total, then you can immediately tell for this first person whether they will be satisfied or not. Because you know there's no one before them, so their B value doesn't matter, but the number of people before them doesn't matter. And you know after them there will be 6 people. So now you might as well take this person, or like you can either take or not take them. Let's say we take them. Now for the second person, you know the second person, we're taking the first person, so this person has to be okay with having someone before them. There's no use to not taking the first person and instead taking this person, because all we care about for this first person is the number of people after them, and they've already satisfied that condition. So for the second person, we're interested in like, are they okay with the number of people we've already chosen? And then additionally, because if they're not, we can't pick them anyway, because there's no reason to get rid of any of those earlier people. And then if they're not okay with that, or if they are okay with it, are they okay with the number of people after, which we still have to pick? So in this case, we've picked one person. If we would pick this person, there would be 5 more people. So they have to be okay with there being at least 5 people after them. And yeah, that's the idea. So classic binary search. We'll do a binary search, write a method to check if it's possible. This method says, just do exactly what I mentioned earlier. So if we aren't okay with how many people we've already used, then continue. And if I have these A's and B's backwards, by the way, so that might be a bit confusing, but I flip them here. If we're not okay with the number of people we still have to pick in order to reach whatever our binary search goal is, then also continue. Yeah, so that's the idea for C. Okay, on to D. Not quite Lee. So in this problem, oh yeah, you have this array. So this is a very confusing problem, but let's talk about it. So you have, we're going to consider an array, what do we call it? Good? Yes. So an array is good if it's some numbers. So these numbers are going to be the length of the substrings. So maybe it might be like 7, 3, and 7's too long. Let's do 3, 2, 2. So this 3 means we're going to pick 3 consecutive numbers. So maybe the numbers we pick are 0. Let's say we pick the numbers 1, 2, and 3. For the 2, we pick 2 consecutive numbers. So maybe we pick -1 and 0. For we pick another 2 consecutive numbers, we pick -3 and -2. We're allowed to pick duplicates here, but in this case we didn't. Now, what you can notice is that the sum of all of these numbers is equal to 0. That makes the array 3, 2, 2 good, because there's some way of picking numbers where they sum to 0. In particular, the 3's cancel out, the 2's cancel out, the 1's cancel out, and then you're left with the 0, which is obviously equal to 0. So yeah, in this case, it's possible. There's another way of doing it, which is you could have a 3, and then you could have this be -1, 0, and 1, and then you could have a 2 be, well, you could have a 2 and then another 2, and these are just opposites of each other. So this is indeed possible for a few reasons. So one thing to notice is that the thing we did here, okay, so let's talk about the question first. The question is like, is this doable? But not just like for the array you're given. The question is it doable for every subset, for all 2 to the n subsets? Excluding the empty set, but that's just a special case, so we can just subtract 1 for that. And we define like doable as, is it good? So count how many of the 2 to the n subsets are good under this definition. So let's talk about what it means to be good. So anytime we have an odd number, it turns out that it's going to be good. And the reason is, if we have just, let's say the numbers have an odd sum, the numbers we pick, then we can pick some range that's centered at 0. So 0, and then this size will be symmetric with this size. So in that case, the sum will clearly be 0. We might have an even sum, though, if we have some odd numbers. And what we can do then is we can pick one odd number centered at this range, and then another odd number also centered at this range. So if we have like a 3 and a 5, and then some 2's maybe, we can put the 3 here, put the 5 here, and then put the 2's, or the other things that have an even sum on this side. They don't have to be matching 2's, right? We can have like a 2 and a 4 as well. And then this can just be some big range, which has an odd sum centered at 0, because you can just combine them all together. So yeah, if we have one odd or we have multiple odds, we can always do it. The hard part is if all of the numbers are even, then what do we do? So sometimes it's possible, right? If you have 2 and 2, that's possible. But for 4, that's not possible. And the question is like, why is that? So now we go into the land of Mathemagic. And it turns out that if you do this, we can look at this slightly differently from what they were given. So let's consider this 3 as like a 0 plus a 1 plus a 2. We can get any set of numbers that the 3 can reach by adding like any multiple of 3 to this, right? So we can add like 7 to each number, or like -7 or like -3, and that would give us any consecutive group of 3 numbers. But here we're like, all we're adding is some multiple of 3. So if we want this to be equal to 0, we want this to be like, we care about this value mod 3. Now in this case it's equal to 0, right? And in fact for any odd number it's equal to 0, but for even numbers it's not. So let's look at 4. 4 would be 0, 1, 2, and 3. Modulo 4, this is equal to 2. And it turns out in general, you can do some math, but if you just do some patterns, it's pretty clear that for number n, this will be equal to n over 2 mod n. So like 0 plus 1 plus 2 all the way up to n minus 1 is equal to n over 2 modulo n. Yeah, so this is the important thing here. So in order to solve the problem, we can say we care about what this, like, okay, so we're gonna add a bunch of these things, and we want like the things we pick, like the numbers we pick here, we're interested in them over 2. We know they're all even, so we're interested in them over 2. And then we're also interested in the GCD of all of these mods. Because if we have like a mod of 3 and a mod of 2, I guess that's a bad example. Let's look at a mod of 6 and a mod of 4. The GCD of 6 and 4 is 2. And if you can add or remove 6 as many times as you want and add and remove 4 as many times as you want, you can get 2. So I guess 6 minus 4 is 2. But that's true like in general when you have it, like when you can go up or down by one number and up or down by another as many times as you want, their GCD is like the net value. That's like the finest you can move. That's just like kind of a well-known thing. So Yeah, we're interested in like these values modulo the GCD. Okay, so now the question is, well, if we pick a bunch of numbers, what is the GCD? The GCD might seem like it's a very complicated thing to evaluate, but it turns out all of these numbers are even. Which means to some degree, all we care about is the number 2. They all have 2 as a factor. Yeah. Well, okay, this might be sketchy. I don't know. It's possible I got hacked on this. I just realized my proof is not totally right. I did pass system tests. Okay. Am I still red? Did I lose red? Yeah, I'm fine. Oh well. Okay. We can earn it back. Yeah, so okay, I don't know why 2 is the only factor you care about. 2 winds up being the only factor you care about. Oh, here's why. Because if you had any odd factors? Oh, because everything does have a factor of 2. Yeah. And you might have factors of other things as well. But we'll see in a bit. Okay. Yeah, so this idea might not be totally right, but I'll talk about it anyway. So, okay, we know everything is even. Dude, this is way harder than the next problem. Let me tell you that. Yeah. Okay. So we. Oh, hello. We have like some array of things. We know everything's even. We're going to pick some subset. We're interested in like how many subsets can we pick so that the sum of values divided by 2 is divisible by the GCD of the values we're picking. So there are kind of 2 cases here. Let's say we pick at least one value where it has a factor of 2 but not 4. So if we divide everything by 2, we can consider this a 1. So we pick at least one value who's like that's odd, right? At least one odd value. Now, this thing, since it's odd, means that the GCD will be able to divide out like everything, right? So if we pick a second number, then the GCD is 2. And as long as we pick like an even number of these odd things, then we should be good, right? So yes, this is hard to explain. So we've got like a 2 here, right? This is a 2. The number this contributes to the sum is 2 over 2, which is 1. So if we pick 2 2s, then these will have a sum of 2, right? If we pick any even number of 2s, their sum will be even. Their sum over 2 will be even. Which is what we're looking for. And we know this will be good enough because since we picked at least one 2, the GCD will be 2. It's also possible we don't pick any 2s, and in that case, we know the GCD won't be 2, it'll be at least 4, because we know everything is divisible by this 2, because everything's even, and then also by at least something else. So in that case, we can recursively solve the problem over here, but that's only if we pick no 2s. If we pick at least one 2, anything that's a multiple of 4, right? So any like 4s or 8s or 12s, any of those things, which are divided by 2, so now they're even, so any 2s or 4s or 6s, any of those things we can pick freely because they won't affect the sum, because we know the GCD will be able to handle them anyway. So we have free choice there, and we just have to pick like an even number of 2s. Okay, that's like a very complicated way of explaining it. I don't know if that made any sense. But also, It's a confusing problem, man. What can I say? So yeah, the idea is like, if this is the first time we're considering it, then we can either pick at least 1 odds, or we can pick 0 odds and then consider everything divided by 2 and then handle that. So otherwise, we're considering the things like divided by 2 or by 4 or by 8 by some power of 2. And we have a couple choices. Either we can pick 0 odds, or we can pick an even number of odds and then pick some of the evens, but we don't care. If we pick 0 odds, then things get divided by 2 for the next round. And if we pick an even number of odds, that means we know the GCD is going to be like able to handle anything that's even. So we'll tackle that. Yeah, this is yeah, the explanation wasn't great there. I'm sorry. I guess I don't understand this math quite as well as I thought, but I guess well enough to write a correct solution. Yeah, I struggled with this for probably 2 out of the 3 hours of that contest, so it was rough. E. E is a nice problem. E is good. E is nice and easy too. Okay, so we have some integers. We consider some array terrible if there are more elements bigger than the mean than there are less than the mean. Strictly more elements, strictly bigger than the mean, than there are elements strictly less than the mean. So they give you an example here. The example is 1, 4, 4, 5, 6. In this case, the mean is 4, and the elements that break it are this, because these two are bigger than the mean, this is smaller. So the thing to notice here is that it turns out you can do this with this, but you can also get rid of the 2 4s. And now 1, 5, 6 is what breaks you. In fact, it turns out this is, like, you only ever need 3 elements, right? If you have a group of more than 3 elements that breaks you, you might as well just pick the 3 ones that are interesting, and those will break you as well. So yeah, the claim that I'm making, my conjecture is that if there are, or if an array is mean, then there are 3 elements in that array where you can ignore everything else, and those 3 elements alone would be mean. And I'm pretty sure that's true. In particular, you would use the 2 biggest elements and the smallest. Those would be the ones that matter. So yeah, just the 2 biggest and the smallest in any set. Or, not necessarily the 2 biggest, but 2 consecutive elements and the smallest. You might have like 1, 4, 5, a million. So 5 and a million, or 5 and 100 wouldn't work, but 1, 4, 5 would. So yeah, you're gonna pick 2 consecutive elements and then the smallest element. Now, this will happen whenever you have the case of like, you have some difference here of 3 and then some later difference that's smaller than it of 1. So you can't ever have the case where your differences between like 2 numbers and then a number and a third number like decrease. The differences have to be at least increasing, and it has to be even more extreme than that. We can't have 1, 2, 3, 4 even though you might be like 3, the differences are all 1. The differences between 1 and 3 is 2, and then 3 and 4 is 1. So the smallest this can be is like 1, 2, 3, 6, and then 1 to 6 is plus 5, 11, 1 to 11 is plus 10, 21, 1 to 21 is plus 20, so this would be 41, right? And these numbers are growing exponentially. So you can have like at most like 31 numbers here before they will pass your 10 to the 9 bound, which makes it really easy. All we need to do is brute force the first element and then greedily pick after that. So yeah, one thing I thought about wrong when I was considering the problem is you can't even have multiple 6s in this case, because the 6s have a difference of 0. So 6, 6, 1 would break you. And I didn't consider that for a minute. Maybe the example they gave me in the problem tricked me up. So good job there. But yeah, this is like pretty clean to implement. Once you know the smallest, you just like use a tree set to find the next smallest one. Now, for some silly reason, that DLE is in Java. And the silly reason is they set a 1-second time limit. They should have just set a 3-second time limit, right? There's like, the n squared is not gonna pass. Make n a million, make the time limit 4 seconds, like, please. But fine. They don't like the tree set, so you can do a binary search instead. But it's still dumb. Like, the time limit is just too tight. It's silly. Okay, anyway, that is the contest. This has been an insanely long video. I apologize for my bad solution to D, but, you know, you live and learn. And I'll be working on F. To everybody who celebrates Thanksgiving, happy Thanksgiving. Hope you enjoy time you spend with your family. And if you don't, then I guess just have a good week. Enjoy your Codeforces practice or whatever else you do during the week. Thank you for watching, and I'll see you. Goodbye.